Now, in 2, you have a parallelogram. Broke this. We have a parallelogram and we want to find z. So let's just draw the parallelogram first. Here. And we have a line going across here. Well, look who showed up. Oh, sorry, it's not quite like that. It's more like this. Okay, and then this is all x, y, z, w's there, and m's in the middle here. And we would like z. So z is OZ, which equals xy, which equals y minus x. So that's the first one, the first part. Next, we want w. That equals OW. That equals OZ plus ZW. That equals Z plus 5/6 ZX. Because in the question I tell you that this distance here is 5 times bigger than this distance here. That equals Z plus 5/6 y minus z. That equals z plus 5/6y minus 5/6z. So that equals 1/6 z plus 5/6 y. But we can use this result here for z. 1/6 y minus x plus 5/6 y. So that is 1/6 y plus 5/6 y minus 1/6 x. So that will be y minus 1/6 x. Don't know if that's right. No, it's different here.
How do you know what?
Where? Which where? Oh, 5/6?
Yeah.
Oh, because in the question I tell you that this here is 5 times bigger than this.
Yeah.
So that would be from here to here is 5/6 the total.
And how did they find 2/3 in the book, the outside?
I said it was just. I just said 1 minute ago was wrong.
Is it?
I think so, yeah, because this is what I got. Unless I made some mistake here. Okay, the next part, M. So, M equals OM, which equals OW plus WM, which equals W plus a half WY, which equals W plus a half Y minus W, which is a half W plus a half Y, which is a half Y minus 1 over 6X, because that's what I said the W was, plus a half Y. That's a half Y minus a 12th X plus a half Y. So that's Y minus a 12th X. Yeah. Okay, you have that? Yeah? Okay, we'll have a look at the next lesson then, unless there's something else you want to look at. Let's have a look at the next one then, yeah? Yeah?
Is it okay if we just take like W plus half WY?
And what? Nope, because the question says give the answer in terms of X and Y. And or X and Y.
Yeah, so it's either use X or Y or both of them, right? So
Yes.
if I use one of them, is it okay?
Yes. Yes. Is what?
Okay.
It's not, because I said X and Y.
Or
X, okay, X or Y, no W. Yeah. Yeah, is that clear?
Yes.
Yeah. Okay, let's have a look at the next topic then. Now for this topic, this is when the vectors look more like coordinate geometry from semester 1. It's not convenient to write or to draw pictures every time you want to do vectors. It's kind of annoying. So what we would like to do is have some way of representing vectors which doesn't depend on the diagram. And we do that by introducing these three vectors called I, J, and K. Or sometimes we write them like this. So what's special about these vectors?
They represent certain things.
Everything represents a certain thing. These vectors are all of length 1 and they're all perpendicular to each other. Sometimes we only deal with two vectors, which the physics students will tell you.
Okay.
Ij actually. And it's like this. So these vectors, they all have length 1. Their magnitude. The magnitude is 1. And they're at right angles. And this makes them very convenient vectors to use. Because, for example, well, I could now say something like x equals 2I plus 3j. And I don't need to give you a picture now. You know that I goes here and j goes here. So 2I would be this, and 3j would be this. So the answer for x would be like this, where this is 2I and this is 3j. Do you see what I mean when I say it looks like what we did in semester 1? It's like the x is 2 and the y is 3. It's a similar idea. You just practice one for me. Draw this one. Vector y equals 5I plus 12j. Draw that for me. Now, 5I plus 12j. I need to switch the screen for a sec. Okay, do you have that drawn? Yep. So you should have something that looks like this. Where this base is 5 I's and this height is 12 J's. Like this.
I have a question.
Yeah.
Now, isn't the J going downwards in the original?
It's different if you're drawn in 2 or 3 dimensions. That's why I was turning the laptop on, because I want to get you a nice picture of a 3-dimensional one if I have it here. It does seem strange in the two that they're in different places. While I'm loading it there, I want you to tell me what the length of this vector is. I want to know what is the magnitude of this vector. How long is it? Tom? You can calculate it, you can calculate it. I want the length of it. Are you guessing or are you calculating? Calculate. It's 13. I have my, just so you know, sorry about that, I have my I and J in the 3-dimensional picture the wrong way around. I should have drawn it, this one as the I and this one as the J. Okay. Did we get 13 for this one? Did we get 13?
Yes.
Now, how did you get 13, Ibrahim? Yeah, but what rule is this? Pythagoras. This is actually right angles. This is 5 units long, and this is 12 units long. So the magnitude from Pythagoras will be 13. In fact, we can have a formula for magnitude now. If I have a vector, oh, hang on, pen. Yeah, if we have, the heck. Pen. There we go, okay. If we have OR equals xi plus yj, when you draw that, you have a vector which is x units on the base and y units in height. So the length, the magnitude, which we represent by this symbol, this means the length of the vector, how long it is. We have a formula for that from Pythagoras. It's just square root x squared plus y squared. And also from Pythagoras, if we were in 3 dimensions, where we had x, y, z, then it would just be like this. Not much different in 3 dimensions. You got that? In the example you just did for me, I now want you to give me the direction of this vector. In other words, what's the angle here? Try and do that for me. Give me the angle of that one. What angle did you get?
7.4.
I think that's about right. It should be a high angle. You can say that tan theta equals 12 over 5. Did you do that yet? So theta is tan inverse 12 over 5, which, what did you say? 67? Oh, okay. Well, you could use sine or cos, whatever.
67.4.
Did you get that also? 67? Seems about right. It should be large angle. And this is the direction. Did you get this? You're in radian mode, aren't you? See how I could tell? Yep. Okay. What makes ijk so useful is it makes it very easy to add vectors. For example, here is vector 1. And here is vector 2. What rule did we have last time to add these two vectors together? What is it?
You have elimination.
No, what's it called?
Matrices.
No. In the lesson I did last time, how did we add vectors together? Parallelogram law from the diagram. But you don't need that law to add them together when they're in this form, because they're just like regular algebra. You have 5 i's plus 3 i's, so in total 8 i's. And you have 12 j's and 4 j's, 16 j's. So I know when I draw it, it would look something like this, where it's 8 on the base, 16 height. and the hypotenuse would be 8 root 5. And what did I call this length here? What do we call the length of a vector? Magnitude. So I could say the magnitude of R1 plus R2 equals 8 root 5. What's wrong? What's also convenient about using I and J is multiplying vectors. So in the last lesson, if I want to multiply a vector by 2, what do I do to it? If I multiply a vector by 2, what do I do? Yeah, you draw it twice as big. But if I want to calculate 2r, what do I do here?
Multiply it all by 2?
Yeah, that's all. So, can you calculate for me the magnitude of r? And then calculate the magnitude of 2r. This answer should be twice as big as this. Well, if we do it together, actually, this one will be square root 9 plus 16, which is 5. And this one here will be square root 36 plus 64, which is 10. Square root 100. So it is twice as big. Do you think the angle, the direction will change?
No.
It shouldn't. So let's calculate the direction. So the theta for r, that will be tan inverse 4 over 3. What's that, please? And then the angle for the 2r. So it's the same. Yep. Now, often in the exam and in your notes, it's inconvenient to write I and J and K every time. So when you have a vector like xi plus yj plus zk, we often just write it like this, x, y, z. This makes your vectors look like matrices, which is good because the rules of matrices also work here. For example, 2r would be 2xyz, and for matrices what do? We just multiply everything by 2, 2x, 2y, 2z. Likewise, if I wanted to add vectors together, like 3, 4, 6, plus 5, 2, 1, just like in matrices, each part adds together, so you'd have 8, 6, 7. So it's actually quite convenient to write them in matrix form because the same rules of matrices work for vectors here. Got that? Not yet. Okay, can I scroll down? Now I'm going to give you this problem here. This vector has a magnitude of 2.8282 and it makes an angle, a direction of 45 degrees. So what I want you to do is to tell me how many i's I have and how many j's I have. In other words, I want you to get this here. This is the I part, and I want you to get this part here. Now this really is just a semester 1 trigonometry problem. So I hope it won't be too difficult. I'll give you a minute to try that. So this vector here is x units long, and then this other vector here is y units long. Okay, did you get x and y? Do we have x and y? Yeah? No? It is. And what did you get for x and y? 2. Yeah. And for y? Yeah. So what you can say here is that sine 45 equals y over 2.8282. Now, when you solve that, you'll get y equals 2. A semester 1 problem. You get cos 45 equals x over 2.8282, and when you solve that, you get x equals 2. So each of these are 2 units long. The base is 2 and the height is 2. This is 2i plus 2j. Okay, you have that? Let's see, anything else? Yeah. Okay.